Hi everyone, I am Jerome Emil Morado, and today I'll be presenting the Laboratory Activity 10 Digital Signals and Z Transform. In this experiment, we explored some of the most essential concepts in digital signal processing, especially how digital signals behave in discrete domain and how the Z transform help us to analyze them. We also generated plots of discrete time signals, computed the Z transfer symbolically and numerically, and examined the poles and zero graphically. So let's begin. We import all the necessary libraries. Import NumPy, Matplotlib, and CP. The NumPy handled the numerical sequence. Matplotlib allowed us to plot discrete signals, and NumPy gave us the symbolic computation of Z transform. Also, the SciPy helped evaluate the system response digitally. So, before we plotting, we, we define the symbolic variables by Z, R, and N, as you can see here. Then, we computed the Z transform of the three important signals. The delta function is the Z transfer is simply 1 here. The unit step function, which is Un, as the Z transform is 1 over 1 minus 2 Z over negative 1, while the 3 is the exponential signal. The symbolic results help us to build intuition of why the Z transform is so useful. It converts sequence into algebraic expressions that are easier to analyze. Next, we generated the plotted 2 signal, a unit step and exponential sequence. Is here. The unit step signal was computed by using the NumPy Heaviside of the function, which is here. Then we defined it by exponential decay sequence with R equals to 0.9. Then we plotted by using the stem plots. The unit step plot shows sudden activation of n equals 0, while the exponential plot shows a decaying sequence of start of 1 gradually approaches to 0. Then, by Z transform using SciPy, we next use SciPy to complete the digital system representation of the sequence, which is B equals to 1, and A underscore then equals to 1 and negative A. Using signal DLT and signal dstep, we generated the first 20 values of the sequence. The plot confirmed that the sequence decays smoothly as it increases, matching the expected behavior of 0.5. So we inverse the Z transform by using this gave us the value that matches the sequence we generated earlier, confirming both symbolic and numerical approaches to produce the same result. And finally, we computed the poles and zero of the system, as the resulted show as A0 at 0 and A pole at 0.5. As we plotted this on the complex plane and included unit circle as the reference, the pole at 0.5 lies inside the unit circle, meaning the system is stable. As we visualize this, it gave us a clear understanding of how pole locations relate to the system's behavior. So as we summarize our activity 10, we learned how to generate digital signals and compute their Z transforms, both symbolically and numerically. We explored the unit step, exponential sequence, and system response using SciPy. We also analyzed the poles and zero graphically and reinforced on how this concept relates to the system's ability. The Z transfer remains one of the most powerful tools in digital signal processing, and in this laboratory activity gave us an experience in applying it. And that includes my presentation of Laboratory 10, Activity 10, Digital Signals and the Z transfer.